Good afternoon, everyone. Thank you for joining this technical webinar. Today, our guest, Hugo Rodriguez, is going to discuss the role of the bond slip mechanism in the seismic performance of existing reinforced concrete structure built with plain reinforcement bars. But before I hold the presentation to him, let me quickly brief you about this technical webinar. Some of you are already familiar with that because I see some names that are familiar to me. So this session will be recorded, and after the approval of Hugo, it will be placed on our YouTube channel, so probably somewhere next week. During the session, your microphone will remain muted to avoid any background noise disturbance, but there is a chat box where you can type your questions. And at the end of the presentation, I will scan through, and if I see that some of the questions are relevant for the audience and related to the presentation, I will raise these questions to Hugo, and then you will decide if he can answer on the fly, or eventually he may get back to you per email. So, on behalf of DIANA, we are very happy to welcome Hugo Rodriguez, who is Associate Professor in the Department of Civil Engineering of the University of Aveiro. And we are very happy to have him today as a guest lecturer for this technical webinar. So, Hugo, if you can unmute yourself, the stage is yours.
Okay, good afternoon, everyone. I would like to start here my presentation. I will turn off the camera to improve the quality of the connection. So first of all, I would like to thank DIANA for this invitation. It's a pleasure for us and a good opportunity for us to share some of the work that we have been conducting here in Aveiro and also in Porto in the last years, in particular in the seismic behavior of reinforced concrete structures. I should say that I have, in the end of this presentation, more questions than conclusions, more open issues than closed issues, but I would say that this is the main reason for our work and for our interest in the topic. I should say that I'm doing this presentation. So my name is Hugo Rodriguez, that's Jean-Claude, and first of all, also thank you to Jean-Claude for this brief introduction and for organizing all the session. But I should say that this work was also conducted by Payman, which is a PhD student from the Civil Engineering Department, and he was the main conductor of a huge part of this study, but he also considers the collaboration of Professor José Melo and Professor Humberto Varun from the Civil Engineering Department of Faculty of Engineering of the University of Porto. In fact, this work comes from good collaboration that we have been having in the last years, in particular in a work where this project, where this work is included, which is a project entitled Assessment and Retrofitting of Non-Seismically Conforming Existing Reinforced Concrete Building Structures and Validation of Corresponding Eurocode 8 Part 3 recommendations. So this is a project that is led by the University of Porto and considers also the participation of the University of Aveiro with our work, that some part that I will present today, and also from the National Laboratory of Civil Engineering, where I will share just a slide of a part of the work that we have been conducting and also in this topic, and I will say that I will have more data and more information in the near future to go really for the global scale. So I present the topic as from local to global, because our idea is going from the local behavior to the global structural assessment. I will present some information that we have already obtained at the local level and also at the element level. And when I say element level, it's at the beam column joint level, but our aim is also to go to the structural level, to the full frame level. But I would share just a slide with that information in the end. So our main motivation is related with the damage observed in recent earthquakes, where we can see the high vulnerability of some reinforced concrete structures, some of them constructed with plain bars, and some of them with plain bars, but also with that were built in the 70s prior to what we call the current seismic design philosophies. So we see here a lot of beam column joints with deficient behavior, some lack of detailing in the elements, the lack of transverse reinforcement, reduced amount of longitudinal reinforcement also. So we see here no details in reinforced concrete elements, in particular beams and columns, but mainly and also quite important in beam column joints. For example, this building here in Italy, where we can see the soft story failure, of course, but the main damage is then concentrated in the beam column joints. And if we look in detail, we can see some of the details that are failing, and the deficient behavior is governed now by the beam column joints. In the previous pictures, we have pictures from Nepal, from Spain, from Italy. So all around the world, this problem is occurring. So to conduct this work, we have focused on two things that I will discuss here. First is a group of tests that we conduct on reinforced concrete specimens with pull-out tests to characterize the bond slip behavior and to find parameters to these models. What is the parameters, or how these models can adjust to our pull-out tests. And then, based on some of these parameters, we try to apply the similar models in the representation of a beam column joint, and to understand the influence on monotonic loads and also on cyclic loads. And this is the main objective of this work, is to get some information how we can do the experiments, take information from the experiments to the numerical models, and how these models are able to represent the global behavior or the behavior of the structures. Of course, there are a lot of open questions, open parameters that we need to discuss, that we need to find points that allow us to use it, not for calibrating numerical models, but to use them in the future. There are a few studies to characterize the bond slip mechanism in structural elements. In fact, a reduced number for plain bars, for ribbed bars or deformed bars, there are more. And a few expressions that allow us to find this constitutive bond slip relationship for the plain bars. We can see here some expressions from the FIB model, where we can see here some information related with the bond stress for good bonding conditions, for poor bonding conditions. We know that most of the models consider here after peak a constant, or even with some increase of the bond stress after reaching the maximum slip. But looking to some of the experiments, some authors like Eliganhausen in the past, even for deformed bars, and later Verderam et al. For plain bars, considered it was important to have a softening after the peak. So with a plateau, like the first proposal from Eliganhausen, and later on from Verderam, where for plain bars, he understand that this peak was not really observed in the experimental tests, and he proposed here a softening behavior right after the peak. And we know the parameters that are influencing the bond performance. They are well known, and we want just to discuss some of these aspects. So we select here an experimental campaign on pull-out tests that was conducted here at the University of Aveiro, namely by my colleague José Melo. And all these results are published in an international journal, so you can access to the results if you want. This is one of my main points in the end of this presentation, is that we have a lot of results available, and it will be good to share results and also the models, so we can discuss and find different ways or find different things to have in mind with this problem. So the idea here was to study the bond-slip relationships based on these monotonic tests. In fact, they were also performed some cyclic tests, but we have not considered them for this study due to some problems in the results and modeling these tests. So here are the two tests that we have considered. This is the experimental setup. So we have a concrete block with different shapes. This is the EN test, where we have around 5 diameters of embedded length, and here we have the SP, where we go until 30 diameters of the embedded length, and then we apply here a force, attraction force, and we have this pull-out test. So quite a common test. Here are the two specimens, or the two types of setups. So here is the first one where we have a block of 20 plus 10 here on the bottom, plus 5 diameters of anchorage, and here in this case where we have the 45 diameters of anchorage. José Melo have also these results about for 30 diameters of anchorage, but we have not considered them in this study. And here's some information about the materials. The concrete strength is quite small, quite low, but is to represent the poor concrete strengths that we found in the old structures, or in some old structures, and then some information about the plain bars that we have considered. Okay. Also in the study, they will use some deformed bars, but I will not present this at this point. If you need, and if you like to have these results or to discuss it, you can share an email with us, with me or José Melo, and we can find a way of sharing these results. So this is basically the results that we have here for the SP test. So this is the monotonic, the pull-out curves, monotonic curves, and we can see here for now the average curve, the mean curve is always present, and is the one that we are using for the calibration of the numerical models. And we can see that in fact for these results we have here this almost linear branch, and when we reach the maximum point we have this softening behavior and then a plateau. So more close to what Eleghanhausen and Verderame have proposed, so probably makes sense to have this type of models. When we look to the models available, there are several models available in the literature. In particular, we have looked, and it's the reason why we are here today, is related with the DIANA models. And there are 5 models that are able to represent this nonlinear behavior, okay, this nonlinear relation between the shear traction and the shear slip, namely the FIB, that we will call it FIB-CEB 2010 model, the Shima bond slip model, the cubic by Doer model, and the power law by Noah Kowalski model. There is another Shima strain model, but we have not considered it here in our study. And also we have here a list of parameters that are needed to be considered during the definition of each model. Okay, so I can go quite briefly in detail. Of course, you have, I tried to put here the links. I can share the presentation. Of course, the video will be recorded, but if you want to drop me an email, I can share the presentation with all the links for the things that I'm mentioning here during this presentation. So we can see here first the cubic model by Doer, where we have a polynomial relation between the shear traction and the slip. And after a limit that is defined here, this will, after this limit being reached, we will have a plateau. Okay, so these parameters here, we need a parameter C, which is related with the tensile strength of the concrete, and also a shear slip where the plateau starts. We need to give these values to the model to define the model and the slip model. Then we have also the power law by Noah Kowalski model, where we have this initial shear stiffness is kept linear to avoid some unrealistic high stiffness when the slip is quite small. And then we have the power law, and we can see here that is mainly dependent on this A, constant A, that is not clear, at least for us was not clear the value of this A. In the literature we found some references for common rebars around 0.4, 0.38 the compressive strength of the concrete, then a power B, which is here a constant, and also the shear slip where the curve is truncated. And with this we can define here not a plateau, but with some increase here after the this point here around the A. Then we have the Shima model. Okay, again the initial stiffness is considered infinite to avoid some numerical issues, and the curve is given by this expression where we need to give compressive strength, the bar diameter, and here a factor to the shear stress, which in fact is an optional scaling factor to the shear traction value. It's a scaling value, so we use it to adjust the shape of our curve usually, or from my point of view ideally should be 1, but in some cases we need to adjust for a lower or higher value to adjust to our experimental curve. And then finally we have also considered the FIB and the model that is included in the model code 2010, and is a curve more close to the Elinghausen model. We have here an initial curve, then a plateau, and then a softening parameter, and then a residual capacity. Of course, we can reduce here this quite to make S1 and S2 quite close to avoid this plateau and to have a behavior more similar to what we have in the Verderam model, if you remember. But of course, it's a model that will need some additional parameters because the backbone is more complete, and there are some relations available in the literature, some proposals available for the S max, the alpha for a 0.5 value, and here the maximum bond stress with some value around 0.3, the square root of the compressive strength for the concrete in cylindrical concrete compressive strength, and 0.15 if we have poor conditions. Of course, these are values, these are properties given by some documents, by some studies, and we always take advantage of this. Then we also take advantage of a new or a capability of included in DIANA, which is to define a multilinear model for the bond slip curve. So in fact, we can define our curve with a multilinear model. And we take advantage of a model proposed by José Melo in the work that I have defined, that I have referred, which is an evolution of this Verderam model. So we have here the Elinghausen or something similar to the CEB model. Then the Verderam proposed here a linear branch, and José Melo proposed here a polynomial branch. So if you remember our experimental results, this polynomial branch seems to have a better approach to this point, and this was the idea of adjusting here a curve. Of course, it's better from the scientific point of view because it seems more accurate, but the definition of this curve is a little bit more tricky, more complicated because due to the set of equations. However, we have here properties like the L of the length anchorage, the diameter, and so on. So it's not that hard to have this coded in an Excel file like we did. So we were able to define an additional model that we'll call Melo et al. Model, and we have defined it on DIANA as a multilinear model, and we have here the curve defined until we want. And this is also the model that we have considered. Then we start modeling our experimental tests. So until now, I presented the experimental tests on the pull-out experimental tests. We have the models available, so we decided to test what are the parameters needed to use these models to adjust to our experimental tests. Okay, this was our first thing. So we take advantage of, and I will not go in detail how to model these tests, because you have a very good video in the tutorial series of DIANA, the bond slip models in DIANA. It's a very, very good tutorial that will guide you during the modeling of this type of tests. So we follow exactly the same tutorial, so I will not spend time here repeating the same things, but just to state that we use the concrete model with a total strain-based crack model, considering the properties that we have for the concrete, and then we start modeling the different bond slip elements, bond slip models for the different tests. Of course, we were adjusting our parameters to fit in the best way the experimental results that we have. So in the end, we have 30 finite element models that were developed for the EN and SP specimens for 12, 14, and 16 rebars, with these 5 different bond slip models, and the concrete blocks were restrained in the 3 sides, and we apply prescribed deformation to have the monotonic displacement, and in the end we have these bond slip curves that we compare with the numerical analysis. Here is the table that we reach with the bond slip models parameters obtained in the end. Okay, we have a recent paper published in Concrete and Structures with all these details, so if you want, you can find a little bit more detailed information about what I'm talking here. And we can see here that in some cases for the different models, of course, we have similar parameters that can follow all the models, some small variations, so on. So in the end, we think that we have here a set of parameters that at least if we need to model something, and that's why we give the next step, that if we need to model a beam column joint or a structure and we want to include the bond slip in our response, at least we have here a group of parameters that can be a starting point for this. Some of them have already some values recommended in the literature, some of them don't, so that's why we decided to do this, and we performed the analysis. I will not show in detail the results. Here is just the displacements during the pushover. So and if you want to have more details about the traction forces and so on, well, we can check the paper, or we can ask us the models. We have here an open way of sharing the things, so we can share the models with all the information. I'm just showing here the basic results that we have. And when we look to the results, we can see here some of the main conclusions that will be repeated for the EN specimens and for the SP specimens. Okay, remember that only the length, the anchor length, is different from the two different test setups. And we can see is that the Noah-Kowalski model portrayed the weakest trend, not aligned with the experimental tests in most of the cases. Okay, we have here a problem adjusting the model to our experimental results. Of course, probably different results can have a better adjustment. I'm not saying that the model is not okay. I'm just saying that it was not adjusted to our results. And in the other way, the CEB, Doer, Chima, and Mellow model have a good representation until we reach the maximum bond stress and accurate slip at the maximum bond stress value. Of course, these points were adjusted when possible, but if you come here again and you look later on to these parameters, you'll see that they are more or less consistent, and they were adjusted, but not that much. They make sense. All these results make sense when we relate with the experimental properties from the concrete, the diameter of the bars, and the information that we have. So what we can see here is that with these models, we can have a good representation of the maximum bond stress, and with some information we can point the maximum slip value and the bond stress in the right point. And of course, due to the model configuration, to the bond slip model's configuration, the post-peak softening was only captured with the CEB and the Mellow model. Okay, if you look here, this is a good example. The experimental curve, it's here in black. Okay, I don't know if this is too small in your screens or not, but here we have this black dot, black dash curve of the experimental results, and then we have here in red the CEB. If you notice here, we have reduced the flat plateau on the top almost to zero, because it was not observed in the experimental tests. So we have here more or less good representation. Of course, now we can decide if you want to stop here and where we want to stop and where we want to make this softening behavior, this post-peak behavior we can control. But if you look, we can see here that only José Melo, and even in some cases better than in the others, can follow the trend of the experimental results. Of course, if you look here to the SP for bars of 10, 12, and 16, the diameters, similar results can be followed. In fact, in this case, the Nowakołowski model was able to reach the similar trend. Again, all the models present a good behavior. Here, the Mellow model presents a lower stiffness when compared with the others, which is a problem that we could adjust here the value of the slip to have a better representation. Okay, we could push this point to the right position, but in fact we were using the values proposed by José Melo on his papers, so that's why we want to check how this works here. And in the end, we can see, if we look to the comparison of the envelopes of the energy that is in fact, we can link this energy and associated to the energy required to debond or to pull the reinforcement. We can see that the ones that present similar energy are the FIB and the Mellow model, basically due to the post-peak behavior. Okay, I would say that this at this point seems quite important, and as you will see in the next slides, for the cyclic and full analysis, this will lose a little bit of importance, this higher energy here presented. So calibrating this, having a set of parameters and much more information, I will invite you to read the paper and to go over the results that we have. We think that we have at least a set of parameters that we can use when we want to do some global analysis. So we use some tests that we have been conducting here. These are an experimental test on full-scale beam column joints. Okay, you can see here a picture of the lab here at the University of Aveiro. This study aimed to study the influence of smooth steel to concrete bond slip mechanism in beam column joints that represents a typical construction from the 70s, okay, without seismic detailing, with and without plain rebars. So we have tested with deformed rebars and with plain rebars. And after doing these tests, our main aim, if you remember the topic of the project, the title of the project is to find also efficient strengthening and repairing solutions for this type of structures. So now we have conducted the tests, and we will do the repairing and retrofitting of these beam column joints and testing again, and hopefully we can also model the new retrofitting solutions in the near future. So here is our justification of the geometry of our experimental campaign. The idea here is to have an internal beam column joint with a sizes, of course, adjusted to our lab, but can represent a typical frame for a reinforced concrete frame structure from the 70s, so mid-height story of 3 meters and the base of 4 meters. So we have here the geometry of the columns and beams, and then the detailing of the reinforcement, where we can see there is no specific seismic detailing and no reinforcement, no transverse reinforcement in the beam column joint. Here are the properties of the materials used. So as I explained, we have constructed 4 beam column joints, 2 with plain bars and 2 with deformed bars, all with the same concrete, a poor concrete, like I explained. And even using deformed and plain bars, the yielding stress is more or less similar. Then the ultimate stress is a little bit higher in the deformed bars, and this is important for the bars of 8 and for the bars of 12. This is important to analyze the results later on, because the main material properties are also different. So after constructing the specimens we have implemented in the lab, this is the experimental test setup used. It will be important to understand later on the numerical model. So we have here the beam column is, the test is performed in the horizontal way. So this is the beam and this is the column. We have here the application of the axial load, which we use 2 levels of axial load. I will explain in the next slide. And then the horizontal deformation is applied here in the column. So we have here the half of the column, so the inflection point of the columns. That's the idea. Here we have an additional length. The column is shorter, the reinforced column is shorter, but we have an additional length to make sure that we have the right inflection point. And then the beams, sorry, I have some problem, is supported here in these elements to make a simple support. And then we perform this with imposed displacements. Here we have an increase of the imposed displacements in the upper column in a cyclic way. We have considered 2 levels of axial load, 450 kilonewtons, which corresponds to an axial ratio of 21%, and an axial load of 305, which corresponds to an axial ratio of 14%. So this is a way of having to understand the influence or the possible influence of this axial load in the behavior of the beam column joint. Of course, to perform the experimental tests, we have the instrumentation, a global instrumentation. I will present the global results, mainly forces and global deformations at the like a force and a drift value, but we have also local instrumentation to have more information about the curvatures, damage distribution, and so on. But not possible to present here all the information, but that's it's an overview here of all the instrumentation that we have. And so we have a full knowledge of the behavior of the beam column joint. And then we perform the tests. Here just an overview of one of the tests, a top view of one of the tests, just to have an idea how the setup works. We can see here the rotation in this point, the actual load being applied, and here the horizontal jack imposing here the lateral deformation through the test, controlling with an external LVDT to make sure that we are measuring the real deformation of the column. And some results that I would like to share. In the end, I will show you. I will look to only to the result of one of them, but we have modeled already the 4 beam column joints. Here you can see some of the comparisons, okay, in a global way, IP1 and IP2. So if just to have this in mind, IP is plane bars, ID deformed bars, 1 high axial load, 2 the lower level of axial load. Okay, so we can see here global results. We expect that if we have a slippage, the force transfer mechanism is affected and might lead to a reduction of the stiffness and dissipation energy capacity of the structure. This is what we expect. And when we look here to some of the results, I would say that I highlight some of the most important results. Of course, there are many other things that we can observe here. We can see that both when we compare IP with ID, so plane bars with deformed bars, we can see that they have similar strength, ID slightly higher, probably due to the characteristics of the deformed reinforcing bars, that the strength, the yielding strength of the deformed bars is a little bit higher. One important thing is that in the deformed bars, the maximum strength is captured much early for 25 millimeters and 45 in the beam column joints, ID1 and IP2. And when we look to ID1 and ID2, and when we look to the plane bars, is captured much later, so at 45 and 60 millimeters. So this related with this comment that I was having here, that this transfer mechanism leads to a reduction of the stiffness, and the maximum value occurs for a little bit later. The stiffness in the beginning, before the cracking, is similar in all the specimens. This is expected, of course. And after the cracking occur, the deformed bar specimens, the ID specimens, show a little higher stiffness, okay, values during the cyclic load. Of course, I will show you the envelopes in the next slide, and this is a little bit clear. However, this is some observations from what we have. All the specimens display a similar response in terms of unloading and reloading, but the strength degradation is more pronounced in the deformed bars. Okay, so when you look to the red result, it seems that the strength degradation here, this post-peak degradation, is more pronounced, especially here, and in this case is more pronounced in the deformed bars. In this case, it's much similar to the plane bars. Looking here to the damages, we have these envelopes and we plot here some points. Okay, so beginning of the cracking in the beams, beginning of column cracking, yielding displacement, beginning of the shear cracking inside the node, detachment of the concrete inside the node, and ultimate strength or ultimate capacity, which is a conventional value, if you want, is the point where we have a reduction of the maximum strength in 20%. And we can see that in both the cracking in the columns, in the beam, sorry, started at 0.1 and 0.2%. Always the cracking of the beams occur first. Then we have the cracking of the columns around 1%, both they are quite similar. And the detachment of the concrete inside the beam column joints is around 2%. And here you can see this post-peak higher stiffness is a little bit higher, but not that important for the ID specimens. And then later you will see that this post-peak, the softening is much more higher in the deformed bars. And when we look to the influence of the axial load in the experimental results, this is not that does not play a big influence. Of course, the IP1 with higher axial load, in fact, have a higher strength, but with a reduced influence. When we look to the final damage, the majority of the cracks are in the beams, always, and located near the stirrups, but this is mainly related with the concrete discontinuity caused by the stirrups. We have this observed in several tests. Then we have shear cracks followed by the concrete spalling in the core joint, and the cracking inside the beam column joint starts around the drift of 1%, like I referred early. And of course we have a huge or higher distribution of damage when we have the ID, the deformed bars, and more concentrated damage with the IP. Okay, in the end, due to the lack of transverse reinforcement in beam column joint, we have always the failure in the joint. All the results that I have talked until now for the beam column joints for these 4 columns are available in a public repository here in the built environment data. This database is available, so you can go there and download, okay? And if you want more information about these experimental results and the modeling of all the 4 columns or all the 4 beam column joints, you can find here, we have here a paper where we publish the experimental tests and also the modeling of the 4 beam column joints to simulate, to calibrate the tests, okay? Not focus in particular with the different bond slip models, but more focus on the calibration with the, in particular we use the CEB model. So if you want to look to the the modeling of the 4 beam column joints, please follow this paper. But in fact, I'm sharing here the modeling of 1 beam column joint. Once again, I will not go into detail of how to model a beam column joint. I would say that this is not the aim of these webinars. Once again, I may advise the tutorial of column beam joint in a portal frame, also in the video tutorial series of DIANA, which is most of the options that were used, we have included in our numerical models. So I will advise you on that, and I will just show here the results that we obtain for the IP1, so the beam column joint 1, with plain bars, where we tested the different bond slip models available in DIANA, like we have done previously on the monotonic pull-out tests. So we have here our experimental setup, the geometry. We have the beam column joint built in the lab. We have looked to the details to check if the reinforcement corresponds to the reinforcement used, and the sizes and the position and so on. We have developed our numerical model in DIANA. So basically developed and meshed in the end. Some of the assumptions I can discuss here. So we apply we have an additional steel plate to apply the axial load and to apply the horizontal load here. And we have also added these two steel plates to make the beam supports. And we have here an additional, because as you've seen, we have here two rollers that allow the beam to be moving in this side. And I'm sorry, an additional steel plate here, because we have the column is shorter, but then we have here an additional element to make sure that we have the rotation at this point. So we need to have here also a steel element, to a steel plate, to make sure that we have the rotation in accordance with the experimental setup. In fact, in the beginning, we were not considering this as a sometimes this make, of course, all the difference to the relative deformation of the relative stiffness between the columns and the beams. Then for the concrete, we use again the same numerical material model. And for the bond slip, we have used again the 5 bond slip models, and we have followed in most of the models the recommended values that we get from the previous modeling for SP12, because it has a high anchorage length. Okay, so we start with this with some minor arrangements. Of course, you have to change the parameters related with the concrete, because the concrete is not exactly the same. It's a little bit higher in the beam column joints. Also, the reinforcement properties are not, the reinforcement steel properties not more the same. So we have make here a minor adjustments, but basically we start as our reference, or we use as a reference the values obtained for the SP12 model. And in the first step, we perform a pushover analysis. Here you can see we have the experimental result here in black, and here the pushover analysis. So we start with the 5 models. We have also considered here a deformed bar, so a common reform. If we forget and we assume a perfect bond slip, we will have here this purple curve to understand here the difference between considering the bond slip or not considering the bond slip in our analysis. So all the models in a global way without tuning, and the results here that I'm presenting, it's important to notice that we did not want to tune the parameters. Okay, of course we could find here a set of parameters that will adjust perfectly to our experimental results. This was not the aim, I would say, of this analysis. So we can say that in a global way, all the models have a good representation of the initial stiffness, which is good. The FIB and mellow models have the lowest maximum capacity. So you can see here, this is the mellow with in this case with the lowest maximum capacity, and the FIB and the other ones without the softening. And that's why I was saying that for the pull-out tests, this softening behavior seems to be important. But now when we go to the full scale with, of course, higher length in the anchorage, this post-peak length does not seem so important. And in fact, the other ones get a little bit more better results. And the Shima model have also a good result. Also, the Duer model have a good result, and therefore we were happy with these results for the monotonic curve or for the pushover curve. Here is an example about the crack width with the CEB or the FIB model, just to see here during the pushover. Most important things, we can see here the detachment around the beams, which is quite important, the concentration of the cracks in the corners, quite similar to what we have in our experimental tests. And also here the diagonal. Sorry, let me finish here just to comment here the result, and also here the diagonal cracking, quite similar to what we have in our experimental tests. So I would say that the damage pattern is similar. The cracks are concentrated in the interface between beam and the joint. It appears, and it will appear also some cracks here in the sorry, but by some reason sometimes this starts moving slides automatically. We have here a similar result with some cracks observed here near the column interface that were not observed in the experimental test, but I would say that this is the minor thing. And we have some diagonal cracking appear in the beam column joint in both cases. So being happy with a pushover, which is quite good because we can run a pushover in a few minutes, even with nonlinear analysis and with this complex behavior, I would say that we can run this in a few minutes. But we try to run also the cyclic load. Of course, this analysis will take a few hours and it's more hard to adjust parameters and so on. So that's why pushover analysis are always good to have this first overview, and we apply this cyclic load that we have. Of course, we have applied just for a part of the analysis to avoid the hours of analysis and the space, and we apply only one cycle for each displacement level. Okay, so this is we have not completely modeled the experimental tests. And here are some results for the FIB, cubic by Doer, Nowowski, Chima, and Mello model. And you can see here that we have in black the experimental curve from the experimental tests, in blue the pushover curve, and in red the cyclic test. Of course, this is important. We are always expecting some reduction when we compare the pushover with cyclic analysis. We are always expecting some reduction of the strength, mainly after the post-peak. But at least for us, we are not expecting so much set differences here, and I would say that we need to work a little bit more to understand these parameters here. But some concerns or some issues related with this, we can see that the FIB exhibits a good alignment in terms of initial stiffness and evolution of the curve, however, with a lower capacity. And the same comment for the Mello that shows in this case the lowest capacity among the models applied. Of course, we know that we could tune these models, the FIB and the Mello model, to other values, not ones that we get from the pull-out tests, and probably we can get, of course, much better results. But that's the idea, and like I explained in the first point of this study. And then Doer, Nowowski, and Chima always with are the ones that, in fact, in this case, present a better approach, a better result in terms of maximum strength. Okay, when you look to other points, namely the unloading, the cyclic analysis, we should state that Doer, Nowowski, and Chima, and also the multilinear have an unloading and reloading law that follows the elastic stiffness until the opposite transition limit is reached. So this is a definition in the software, okay, and after which the bond slip curve is recaptured from the point where it was left in the reverse direction. And the FIB model have a different way of working with the cyclic analysis that was mentioned in my previous slides. So it have different rules to perform the cyclic analysis. And when we look here to a problem that for us is a little bit, it's important, is related with this pinching effect at least it seems that FIB, also the mellow, but in particular the FIB model, seems to capture better this pinching effect. That is clear in all the experimental results, and with the other models, due to these unloading and reloading rules that are implemented for these models, is not able to capture this pinching effect. Okay, so probably this is a good thing to be improved and discussed in the future. So here we can see that the pushover, of course, have higher capacity when compared to the cyclic loss, and the problem here on the post plateau is that is not that significant as it was in the, as it was mentioned in the pull-out tests, and in fact the models with a constant bone slip after the maximum stress seems to have better results. Later on, we decided only to compare, and I know that I'm reaching my time, but only a few slides left. I will show just one or two videos. We compare also the crack widths to have some ideas. Here, just an example. Here with the FIB, I'm just going further, where we can see here the concentration in the beams that follows a similar pattern to what we have in experimental results, and also some diagonal cracking in the beam column joint, which is what we expect. In fact, the FIB was the one with a lower crack width, mainly related with the forces like we observed. But for example, here in the Shima model, we can see here also again the cracks more concentrated in the beams, like we have in our experimental tests, and also the diagonal cracking appearing here in the center of the beam column joint. To respect the 1 hour presentation, I will not show all of them. I will show here just this is for now Kowalski model, but even in different ways we can see that all of them, most of them, can respect and can have a similar trend to the damage patterns that we were observing in our experimental tests. To conclude, I would say that concerning the damage, we can see that in all the models, or in most of the models, we can have the damage mainly with the minor cracks in the beams and in the beam column interface with the joint panel, which is good. It means that the models are able to represent the damage that we observe, and the minor diagonal cracks that appear inside the node, and the failure in the end seems to be in a good way, or in a good representation when we compare the numerical models with experimental ones. Among the models employed, the mellow and the FIB were the ones that show less damage, but of course they have, like we saw in the cyclic analysis, the lower capacity, the lower strength, so this is related with that. Finalize some comments and future works. So like I stated in the beginning, more questions than answers. We think that we have some good reliability on the bone slip models that were employed and verified in the DIANA for the pull-out tests and for the beam column joints, and we have already some properties that will allow us to continue this work now for the next step. They are able to represent these complex interactions, even with plane reinforcement, where this effect is more relevant. And of course, the monotonic tests, or at least the monotonic analysis or the pushover analysis, present a better result. And we still have some questions with the cyclic analysis that we consider that we have a good agreement in terms of results, but we would like to improve. I don't know if adjusting a little bit the parameters to try to understand what could be improved in the experimental results, but also in the end the damage patterns are being captured, what is quite important for us. And we want to, of course, to keep studying this, in particular in seismic non-conforming reinforced concrete frames. It's quite important to highlight, I have not highlighted this in the beginning of my presentation, that to model this type of frames with this type of behavior, where the damage and the behavior is ruled by the joint panel, is quite hard with traditional fiber or fiber nonlinear fiber approaches with the concentrated or distributed plasticity. It's quite hard to capture this nonlinear behavior, so we need to use this type of more refined models if you want to study in more detail this type of frames. And that's why we are trying to use these models in our studies. As the final comment, because the future works are here, we have repaired already our beam column joints, and we will implement retrofitting strategies in beginning of January. So probably who knows if we will present some of these studies, because it's quite hard to have old concrete, new concrete, and the retrofitting strategy after. This will be also challenging for the modeling stage. And like I told you, we are also doing here, sorry, let me just remove the sound. We're also doing this test we're doing at National Laboratory of Civil Engineering. It's a frame with a similar, if you look here, with the similar details of our beam column joints. And we have tested already in the scope of this project in the National Laboratory of Civil Engineering. We have already developed a numerical model in DIANA. We have already performed some pushover curves. However, I would say that we don't have the results yet ready to be presented. So I just highlight here that we are doing this. And it's a quite nice thing, because we have, again, now for nonlinear dynamic analysis, we have quite similar problems. As you can see here, the behavior is being controlled again in the beam column joints, and we want to perform first pushover analysis, but later on nonlinear dynamic analysis in DIANA to see if we can get also these results. I would say that this frame here is with the same, exactly the same details of our beam column joints, just scale to be able to be tested in this shake table test. So I would say that this, to trust in these pull-out tests. Also, my colleagues in FEOP are doing some tests on columns, beam column joints, and then the frames. And if we can calibrate all these numerical models, will help us to have a better and more information about bond slip mechanism and how to model it in this type of frames. Finally, I would like to leave you, thank you for the time. And like I stated in the beginning, if you want to change models, results, and ideas, let us know. We are more than happy to share all the information and to discuss all the problems. Thank you all. And once again, Jean-Claude, thank you for having me.
Well, thank you, Hugo, for this very nice presentation. I mean, that's quite an amount of work presented. And on behalf of DIANA and the large audience, I would like to thank you for your time and presenting this work. I must say that there are a good number of questions raised, so a lot of interest. But since we are reaching the 1 hour time, I'm going to collect all the questions and send the questions to you, Hugo, per email, so you can get back to the people on due time, because it's now a little bit more than 1 hour, so I don't want to exceed that. But thanks a lot for this nice presentation. And yeah, you still have some work to do. So I'm sure that you will have more than enough to present in a next webinar somewhere next year. I will definitely get in touch with you, Hugo, because it was very, very interesting. And let me share. I mean, there are a lot of positive feedback about your great presentation, so people are really enjoy it, Hugo. So one more time, I'd like to thank you for taking the time to present this nice research work, and yeah, quite an amount of data to deal with. So I'm going to conclude this webinar because it's already 4:05. And as I mentioned, I'm going to collect the question, send them to Hugo, and Hugo, I mean, yeah, it will be your freedom to reply to the question. And one more thing I'd like to mention before to end this webinar, of course, keep an eye on our website because there are more events planned in the coming weeks and months. But some of you already noticed from the comments that I can read, we have released a new version, which is DIANA 11. It's available for download since yesterday. It's a major release. A lot have been done in terms of new features and performance in this version. So I really invite you to download it and to challenge it. And we would be more than happy to hear your feedback because our development team has been working for a year on it. And yeah, a lot has been done. So we are excited to hear your feedback as an end user. So I'm going to end this webinar. One more time, Hugo, on behalf of the audience, on behalf of Diana, thank you very much for this presentation. This presentation has been recorded. I will check with Hugo, and hopefully in the coming days we will put the recorded session on YouTube. And keep an eye on our website. There are more events to come. Thank you all. Have a good end of the day or a good start of the day, depending where you are located. And I'm sure that we will see in the next event. Thank you. Bye.